welcome to several of upcoming discussions brought to you by Kyocera SGS Precision Tools. My name is Scott Zukup, and I am the East Region Application Engineer. And today my discussion will focus on machining stainless steel. So we've muted everyone's microphone, as Dan pointed out, so there's just minimal background noise. And then I ask that you hold off on all your questions until the end of the presentation, and then we'll come back. There we go. All right, so many of you out there are dedicated users of the SGS product, and we thank you for your business. For those of you that are not so familiar, let me take a minute to talk and tell you a little bit about us. So SGS manufactures solid carbide round tools exclusively. We do not offer high-speed steel or taps. Our main manufacturing and stocking facility is also our headquarters, in Cuyahoga Falls, Ohio. And our R&D department is just down the road in Monroe Falls. We also have an incredibly successful regrind facility in California and our tech hub in Virginia, which is devoted to engineered solutions and specials. We grind over 11,000 solid carbide round tools a day and strive for a 95% plus fill rate on those standard catalog items. So be sure to check out our website at the Kyocera-sgstool.com. So SGS is a materials-based company, and by that I mean we manufacture general purpose and high performance solid carbide cutting tools designed and tested on specific materials. With today's focus on stainless steel, we'll show some of the elements used to create stainless steel, and then I'll touch on some of the attributes and types of stainless steel used in the industry today, and why some of those materials can be a real challenge to machine. So for a material to be classified as stainless, there has to be a 10% chromium and 1.2% carbon content or less. The base material here is iron, and certain amounts of other materials or elements are added to change the unique physical properties to suit the needs of each industry or market. For example, materials used in food and medical applications have properties that allow it to be easily cleaned or sterilized. The oil and gas industry or energy industry, on the other hand, uses stainless with additives to protect against highly corrosive liquids and high heat and pressure. So even the automotive and high appliance market uses the stainless steel for the durability and the aesthetics. Depending on what elements are added and how much dictates the tensile strength, melting point, oxidation, and corrosion resistance for each type of those stainless. Sulfur is added at low levels to improve machinability and formability. It will form sulfide inclusions in the material, but these inclusions act as chip breakers. It aids in lubrication by forming a thin layer at the cut surface. The additional sulfur allowed the creation of some more common 400 stainless steels and is used generally with the F designation at the end. Machinability varies greatly in different types of stainless steel depending on the elements added. A condition called built-up edge is when the material adheres to the cutting edge and is usually caused by low cutting speed and work hardening at the material at the point of cut. Increasing the shear or rake angle and the RPM will aid in heat creation, but there are many other dynamics in each type of stainless steel. Thermal conductivity is the ability of a material to transfer or conduct heat. This is one of the major factors in machining stainless steel, since it is a very low ability to create the heat necessary to form and break a proper chip. So in machining workpiece with poor conductivity, an increased amount of heat transfers into the tool. So this supports the importance of proper coolant flush to carry away heat and chips, and tool coatings, which acts as a heat barrier between the tool substrate and the material being cut. So moving now into the elements added to each base material to form the various types. All of these alloying elements can be found in the periodic table. Added in different amounts and at different stages of the material development, each one gives the material the different qualities desired. As more and higher amounts of the elements are added, tool parameters decrease and tool life can be compromised. Of course, first up is chromium. I said earlier that a material must include a minimum of 10% chromium to be classified as stainless. During the metal cutting process, iron on its own combined with carbon creates iron oxide, which is basically rust. When chromium is added, the material has the ability to create a passive film called chromium oxide. This basically stops the form of rust and creates an immediate barrier when exposed to oxygen. This is the base of all stainless steels. Carbon is added in low amounts to certain types of stainless to increase the hardness and strengthability. Low carbon types like 304L are used often in welding situations. Nickel is used in stainless to increase its resistance to heat and corrosion. This can lead to poor chip formation at higher levels and increase the cutting temperature even higher than chromium alone. So adding molybdenum improves the resistance to the pitting corrosion, meaning it can be used in more aggressive environments like pharmaceutical equipment, outdoor fixtures and hand railings, marine parts and fittings. The downside is material has an increased ability to work harden, and sharp geometries are the most effective here. Nitrogen is used in place of carbon in high strength austenitic stainless steels. Nitrogen has a greater solid solubility than carbon and is a strong stabilizer. It also improves resistance to the pitting corrosion. Titanium is used to improve the toughness in ferritic stainless steels and hardness in martensitic stainless. This combination can be difficult to machine and high shear geometry is needed. It exhibits strength characteristics superior to typical nickel-based austenitic stainless steels, which makes it best suited for parts that really can't be subsequently annealed after the fact. Niobium is used to increase the hardness in martensitic alloys, which in turn improves machinability. On the other hand, it will increase the strength in austenitic materials and thus chip formation can be compromised. And copper is introduced to stainless alloys to add to the precipitation hardening properties, or it can be used to enhance corrosion resistance for applications in seawater and sulfuric acid. Okay, so here's how some of these different types of stainless steels are formed. Um, these are really defined by the alloying elements and the material's grain structure in the end. As I said, the base to all stainless is iron. When we add chromium, we now have ferritic stainless. These are classified in the 400 series, usually with 10 to 30% chromium, and have excellent corrosion and high temperature oxidation resistance. They cannot be heat treated and are always magnetic. So typical applications for this type of stainless include automotive exhaust systems, heat exchangers, and furnaces. When we take that ferritic material and we add carbon, we get martensitic stainless. Because of its chemical composition, they can be hardened and strengthened through heat and aging treatments. These methods make martensitic steel stronger than other and good choice for fabrication of medical instruments, mechanical valves, turbine parts, just to name a few. The pH stainless falls into this type as well. So we take that martensitic and we add nickel to the mix. We add austenitic type stainless steel. These are classified in the 2 and 300 series usually, and are most popular grades of stainless steels produced due to their excellent formability and corrosion resistance. They're really used a lot in automotive trim, cookware, food and beverage equipment, and a variety of other industrial applications. Duplex stainless steels are called duplex because they have a two-phase microstructure consisting of grains of both ferritic and austenitic stainless steels. They are almost always double the strength as regular austenitic or ferritic steels alone and have very good stress corrosion cracking resistance. They're used extensively in the oil and gas industry. Finally, the super austenitic type. These fully austenitic grades give excellent corrosion and stress cracking resistance. They may also be lower cost alternative to nickel-based alloys, depending on the application. Super austenitic grades are usually for wastewater treatment and chemical applications. So to choose the correct geometry for any stainless, we need to understand the content and type of alloying elements that are going into it. Hardness and toughness will always be an important factor. Once we understand those traits, we can apply that knowledge to identify the cutting tool and the type of tool path we need. The tool's attributes can help or hinder the ability to make or break a chip. The coating is also really important for added lubricity and to reduce the amount of heat back into the tool. We generally apply a positive rake to stainless steels. This sharper edge will shear the chip and reduce friction, which in turn will reduce heat at the cutting zone. If the tool is too sharp though, we sacrifice the edge strength needed for added tool life. So we have to find a balance for the two features for best results. Eccentric ground relief angles provide additional strength and give a sharper cutting action. Traditional facet reliefs are much sharper and will work for a short time, but they wear quickly and they reduce tool life. So variable geometries like unequal flute spacing and changing helix angles reduce vibrations and enhance the tool's performance. Flute count is usually based on tool path and a type of operation for balance of maximum material removal and tool life. Using high efficiency intercoil tool paths will reduce the amount of heat generated and can be very effective in machining stainless steels. The coating on a tool has a few different functions, but in the case of tough stainless steel, we use it as a heat shield. Uncoated carbide exposes the substrate and heat will quickly break down the binders in the carbide. We also use advanced PVT and nano coating to create that slick surface for the chip to slide across, and that in turn reduces heat. Coolant should be applied when the machine is stainless whenever possible. Using coolant ensures that the friction between the surface of the cutting tool and the material is reduced, and lubrication significantly enhances the metal removal process. So I mentioned earlier that we grind and coat over 11,000 tools a day. At SGS, we also have our own coating chambers and formulas. Everything is manufactured and coated under one roof. We offer several high-performance coating solutions that work well in stainless. The first one is what we call our Dynamite A, or TA. This is an aluminum titanium nitride nanostructure PVD coating. This coating provides a very thin, hard heat barrier. It gives added protection from erosion and abrasion. It's perfect for machining stainless steel. Dynamite X, or TX, is our proprietary high-performance nano composite hybrid. It works well in a wide range of materials and applications. It can also withstand high cutting speeds and temperatures. And finally, this is our proprietary Dynamite M, or TM. It's based on a titanium aluminum silicon nitride, and it's easy to identify by its color. That will also offer high hardness for protection against corrosion resistance and abrasion. And it's an excellent choice in machining titanium and stainless steel. So I'm going to move now into the SGS portfolio of high performance tools that we can apply to the stainless. Each one has different advantages over the other depending on the application and the type of tool path we'll be using. First up is our most recent addition to the SGS family of high performance end mills. This is the Series 77, or what we call the H-carb. This 7-flute end mill has an eccentric grind with variable flute spacing. The tool has an optimized core diameter for increased rigidity in the longer lengths of cut. We also offer this tool with chip breakers as a standard. This will aid in stainless steel and create a smaller, manageable chip. So this end mill is designed to be coupled with the latest CAM software that utilizes the constant cut method of programming. Software has many variations or names, but a few common ones are Mastercam's dynamic milling and Gibbs Cam volume mill. So another common term used is trochoidal milling, where the end mill uses a circular motion to create a large swath or slot. These tool paths use light radial engagement at high axial depths, but at increased feeds and speeds. It uses chip thinning to increase the tool life and maximize material removal rates. While being versatile in the material selection, this end mill will excel in stainless steel using the TA coating option coupled with the chip breaker version of the tool. Every market listed here will machine some form of stainless, with medical and power generation being dominant. The offering includes over 500 items with fractional sizes ranging from a 1/4 inch to 1 inch and metric from 6 to 25 millimeter in diameter. Like the cut options for this series include 1.5, 1.5, 3, and 4 times diameter. We stock square corner, corner radius, and chip breaker as a standard catalog item. So 2 coating options are available with TA and TM. So here at SGS, we are committed to saving the customer money. While we rarely win a test based solely on price, we must constantly justify and document cost savings at the spindle. It's all about cost per cut. This is a recent case study based on a cost savings we offered a customer in 13.8 pH stainless. They were originally using a 2-inch face mill, and they took a very light 25 thousandths axial depth of cut per pass. We used a 5/8 diameter H-carb and took the full 1 3/4 axial depth, but reduced our radial engagement to 10%. While the tool cost for the H-carb was significantly higher than the indexable inserts, we went from 15 to 60 parts per tool. Our material removal rate also jumped from 0.25 to 3.9 cubic inches per minute, which brought the customer cost per part from $146 to only $31. So in the end, we saved the customer over $114,000 on this one job. So next we have our most popular Z-carb ever, the 5-flute HPR, or what we call the high performance rougher. So this is the 5-flute version of our flagship Z-carb end mill and has an eccentric grind with variable flute spacing. The tool has unique end geometry optimized for ramping up to 5 degrees in all materials. We also offer this tool with a central coolant hole on select sizes over 1/2 inch. This is really useful when helical ramp milling and pocketing into tough stainless steel alloys. This end mill is very versatile in the sense that we can perform full diameter slotting and sheet finishes down to 80 RA when needed. Robust edge strength allows heavy radial and slotting up to 2 times diameter in certain applications. Very efficient using typical G-code programming or trochoidal tool paths. Like the H-carb, we offer this tool with the 2 coating options. This end mill will excel in stainless using the TA coated option coupled with the through coolant design when needed. Again, every market listed here will machine some form of stainless. The offer includes over 800 items with fractional sizes ranging from 1/8 inch to 1 inch and metric from 6 to 25 millimeter in diameter. Like the cut options for the series include 1, 2, and 2.5 times diameter. We stock square corner and corner radius as a standard catalog item, and we have the 2 coating options as mentioned with TA and TM. So here's another case study based on a cost savings that we offered a customer in 14.4 pH stainless. They were using a competitor's 5-flute end mill with a trochoidal tool path. Both end mills were 1/2 inch diameter, programmed to take 600 thousandths axial depth with a radial engagement of 20% or 100 thousandths in this case. Tool cost was similar and running parameters stayed the same. SGS won this test by increasing the tool life, going from 3 to 10 parts per tool. So this reduced the overall tooling cost from $76,000 down to only $22,500. And in the end, we saved the customer almost $62,000 on this one job. So here's a unique 3-flute tool originally designed for stainless steel applications, the Series 33 end mill. This 3-flute high performance end mill has several attributes that make it perfect for heavy material removal in stainless steel. We start with an eccentric grind with variable flute spacing. We had a variable helix ranging from 32 to 48 degrees. That feature allows us to incorporate a stepped core for added side load strength. The tool has a unique end geometry called symmetrical gashing, where all 3 flutes come to the exact center of the tool. Makes it very, very strong. And although it only has 3 flutes, this end mill has proven to be an excellent choice in all stainless applications, but especially for low horsepower machines and unstable setups. Tough edge strength allows full slotting up to 1 diameter deep in tough alloys. The chips created are pulled up and out of the cut to make pocketing a really easy task. This tool is only offered with Dynamite A coating. It will excel in stainless steel, especially in slotting and high ramp applications. It will fit into all markets listed and can be used in any ferrous metal. With a small fractional portfolio from 1/8 to 1 inch, keep in mind these tools are targeted for roughing. We have a limited offer on diameters and corner radii by design. Metric options are slightly larger because of our global presence and the popularity in Europe. Again, TA coating only. So this test was performed in 316L stainless in the power generation market. This part was a large 6-foot spur gear with 144 internal teeth, and the customer was using a competitor's end mill to rough the tooth profile, with the slotting capabilities of the Series 33, we were able to cut the number of axial passes in half and double the feed rate in the process. The tool cost was similar, but the material removal rate jumped from 1.66 to almost 5 cubic inches per minute. And tool life was also increased from 3 tools per part to 2 parts per tool. So that equated to a 500% increase. In total, the customer realized about a $20,000 cost reduction based on only 46 parts per year. And next up, we have our T-carb or Series 51. This end mill features 6 unequal flutes with a fairly radical eccentric grind for edge strength. The 41-degree helix works very well in stainless applications using high-speed machining methods. The enhanced 6-flute design of the T-carb end mill offers virtually chatter-free machining. Center cutting allows for ramping up to 3 degrees in most materials. It excels in titanium and stainless steel using the trochoidal or helical interpolation tool pass. Also a great multiple flute tool for finishing in all ferrous materials. This tool is only offered with the Dynamite X or TX coating option. Applying similar materials to the H-carb and HPR using the light radial passes at exceptional feed rates, similar programming methods. This tool can be used in all ferrous materials, and every market listed will machine some form of stainless, as I said before. The offer includes over 140 items with fractional sizes ranging from 1/4 to 1 inch and metric from 6 to 20 millimeter in diameter. Length options for this series include standard 2.5 times diameter length of cut, and it's also available with a stub length of cut with a neck relief for long reach applications. We stock square corner and corner radius as a catalog standard item. And again, it's offered only with TX. This case study is based on a cost savings we offered a customer cutting A286 stainless in an aerospace. They were using a competitor 7-flute end mill with a trochoidal tool path. Both end mills were half-inch diameter, programmed to take 540 thousandths axial depth of cut with a radial engagement of about 7%. Tool cost for the T-carb in this case was slightly less, but we did increase the chip load from 0.0018 to 3 4/10 inch per tooth. So that equates from 15 to almost 28 inches a minute. SGS won this test based on the reduction of cycle time. And in the end, we saved the customer almost $40,000. Well, moving now from end mills to our most popular drill. This is the Hypercarb Series 135. We offer some very unique features on this high performance drill, with the most important being that it's a double margin design. You notice a secondary gullet behind the primary flute. Top it off with a very robust 145-degree split point and enhanced edge protection. The high performance flute design coupled with the double margin gives the drill the ability to create a reamer quality hole without through coolant. The coolant is delivered to the cutting edge by the secondary flute between the margins. Specialized point allows high penetration and low thrust, thus reducing horsepower at the spindle. This drill also excels in cross-hole and core hole applications because of the strength of the core and the cutting edge. Materials include all ferrous and even non-ferrous applications in every market segment. The offering includes over 450 items in 3 and 5 times diameter length of flute. Mixed fractional and metric sizes ranging from 1/64 to 59/64 on all common fractional and metric shanks. This unique drill is only offered with Dynamite A coating. So this final case study is based on a cost savings we offered a customer in 304L stainless. They were using a competitor's solid carbide drill with flood coolant. Both drills were 3/16 diameter, programmed to take a short 300 axial depth of cut. Tool cost was similar, but the running parameters went from 2970 RPM at 3 thou per rev to 3700 at 4 thou per rev. And SGS won this test by reducing the cycle time and increasing tool life, going from 2 to 50 parts per tool. So that reduced the overall tool cost from $21,000 down to $835 for that job. And in the end, we saved the customer almost $22,000. I need to point out here that every case study you saw today and all case studies for every application are available to download as a PDF from our website. They're stored under the Resources tab. It can be researched by industry, material, or SGS tool series. These case studies can be used at all levels of manufacturing to spur conversation with customers or management even to qualify the need or desire to find a better solution. So print them out, share them with colleagues, and use them to really shine a light on opportunities for improvement. Also, if you're not familiar with it, this is an introduction to our online application assistant and calculator. We call it the Tool Wizard. You can use a Tool Wizard to help choose the right tool for the job or simply get more precise starting parameters based on your specific material or application. It's a great tool and I encourage you to check it out. So to wrap this up, let me summarize the things you need to successfully machine stainless steel materials. First, understand the alloys within the hardness of your specific material. Next, determine the type of machine and tool paths you use to run the job. Third, select the type, geometry, and coating of the tools you need based on the material makeup and the tool paths you selected. Number 4, confirm starting parameters by catalog rates or use online calculators. Next, make sure the coolant flow is adequate and check concentrations and cleanliness. It's very important. And finally, don't hesitate to call someone for help. There's a ton of information online. Sites like matweb.com, they show hardness and alloy content for just about every material available. So you can also reach out to your local SGS rep or distributor for more information. Use your resources wisely. We're here to help you succeed. So in closing, everyone here at Kyocera SGS want to thank you for your time and your business. And we hope to all see you again on subsequent discussions.
How do we find our local rep in our area?
Well, maybe you can answer that, Dan, through the website, possibly.
Yeah, so Deanna, the answer to that is on our website. If you were to go to the distributor search page, you are able to search via your state if you're in the United States, or your country if you're outside of the United States. And on the state or the country page that you select, you'll be able to find your local sales engineer and or sales rep and any of the local distributors in your area. I hope that answers your question.